Alright, so welcome back. We just got done talking about density, and hopefully you've tried problems 1, 3, and 5 on your own. However, if you haven't, I'm here to work those with you. So, number 1 from page 343, chapter 13 says a 100 milliliter beaker holds 120 grams of liquid. What is the liquid's density in SI units? And so we know that SI units are kilograms, right? Let me go back here. So we know that SI units are kilograms per meter cubed. And so when I'm looking at SI units, I want kilograms per meter cubed. But here they gave me grams and milliliters. The good thing about milliliters is that I know 1 milliliter is also equal to 1 centimeter cubed, right? And so I do have a conversion for grams per centimeter cubed, right? One of these is equal to 1,000 of these. And so I'm going to start with my initial density formula that the mass density of something is equal to the mass divided by the volume. Here we've got 120 grams per 100 milliliters, which I am just going to call 100 centimeters cubed, right? And when I work that out, I should get 1.2 grams per centimeter cubed. I'm going to times this by 1,000 because I know there's 1,000 kilograms per meter cubed per 1 gram per centimeter cubed, right? And so these two units are going to cancel and cancel, and I'm left with what I want. And when I do multiply that by 1,000, I get 1,200 kilograms per meter cubed. And if you got the same answer, great job. Going on to number 3. Air enclosed in a sphere has a density of 1.4 kilograms per meter cubed. What will be the density of the air if the length of the cylinder is halved, compressing the air within? And so what we've got to figure out right now is how the heck do we get the volume of a sphere? It is listed in your book in the reference pages. You can Google it as well. But the volume of a sphere is equal to 4/3 pi times the radius cubed. And so the first thing that I'm going to do is figure out, right, it's not necessarily intuitive, the relationship between volume and radius. And so I'm going to do a little sample calculation. Right, and I'm going to make up some stuff. And so I'm going to say volume is equal to 4/3 pi, and then I'm going to use 4 as a radius, right, and then I'm going to cube that. And so when I do that calculation, I find that the volume of that object is 268, whatever the unit I'm using for 4 is. Right, and I want to figure out what happens to the volume when I half the radius. And so I'm going to do the same thing, 4/3 pi. This time I'm going to half that radius and cube it. Right. And I get a new volume of 33.51, and again, whatever the units that I'm using for these make-believe things are. I can find that the relationship between these two things, my new one, is 8% of my original one. Right? And so I can divide by 8, and I should get this number. So when I bring that over to my density formula, I get equals mass divided by volume divided by 8, right? And so this is my new transformation of this is how this is going to affect this. This, however, is a really ugly term. I don't like to divide by fractions, and so what I'm going to do, right, is I'm going to say mass is equal to, and I'm going to flip and multiply 8 over V. And then I get this really nice M over V, right, times 8. And so it's the original density times 8. And so when I come over here, I know that my new density is going to be whatever the original was times 8. And so all I've got to do is grab that from the word problem. My original density is 1.4 kilograms per meter cubed times 8. is going to give me my new density of 11 kilograms per meter cubed, right? And if you got that, then you got it right. Touche, good job. Alright, and then last but not least, we've got number 5 on page 343. I am going to just do A. I'm going to leave B up to you, okay? So what I've been given is I've got 50 grams of gasoline, and I've got 50 grams of water. And so when I look at these, I can find, right, the density of those things, and volume, excuse me. So it's mass divided by volume. There we go. And so I can find the density of these things. I know what mass I have, but I don't know what volume those are occupying. And so that's going to be my first goal, right, is to find the volume of these things. And then I know that my final density, or my average density, is going to be equal to the total, I keep doing that up top, the total mass divided by, I'm going to have to put it down here, the total volume. And so I can take my total volume that I do find, plug it in over here, and find the average density. And so we're going to do part 1 of A. Right? Part 1. Part 1 of A, we're going to say that the V total is equal to the volume of gas that I've been given plus the volume of water that I've been given. And when I rearrange the density equals mass divided by volume, to find volume, I'm just going to use mass divided by the density. And so that's what I'm going to come down here and do. And so I've got 0.05 kilograms of gasoline, right, when I do that gram to kilogram conversion. And the density of gasoline is 680 kilograms per meter cubed. And I'm going to add that to, I've also got 0.05 kilograms of water, and the density of water is 1,000 kilograms per meter cubed. And what this is going to do is give me my total volume of 1.235 e to the negative 4 meters cubed. And so I can take this number now and go and start solving part 2 of this, which is that P average, right, the average density, is going to be equal to the total mass divided by the total volume. And so my total mass, when I convert that, is 0.1 kilogram. Right? And I'm going to divide that by what I just found the total volume to be, e to the negative 4, right, which is going to give me a total density of, wait for it, 810 kilograms per meter cubed. Right? And if you got that, touche, good job. I'm going to tell you that part B works a similar way, except this time I'm giving you a volume of these. Again, I know in this case, I know the volume, I know the density, and I'm going to have to find the mass of those things. Other than that, you go on to that second step once you found the mass of all of them, and you're going to find the average density is equal to the total mass divided by the total volume. Works the same way. Okay? Alright, so let's go on to 13.2, which deals with pressure. Pressure is just the force per area. Oh, and there should be a parenthesis there. As always, we're measuring force in newtons, and we're going to be measuring area in meters squared. The SI unit for pressure is pascals, and we're going to revisit this idea here in a second. But pascals is really easy because 1 pascal is equal to 1 newton per meter squared. And so it works out directly with the SI units for force and area. The big idea here that I want you to get is that pressure increases as you go deeper into a fluid, okay? And so this is like as you dive down in a swimming pool, you experience more pressure. Conversely, as you climb up a mountain, you experience less pressure. And the way you can think about this, again, is this book stacking method that I talked about, right? And so if you've got a person who's laying on the floor, and you stack 1 book on top of them, they feel a little bit of pressure. If you stack 2 books on top of them, a little bit more, and so on and so forth. And so you can think of pressure in this, right, as the more fluid I have above me, the more pressure I experience. And so that fluid can be air, it can be water, it can be any combination of the two. And so the more fluid that I have on top of me, the more pressure that I experience. And the really cool thing is that we can find our pressure that we experience at any depth in a given liquid. And so our pressure, the pressure that we will experience, is equal to our initial pressure. And usually when we talk about initial pressure, we're going to talk about initial pressure being at sea level. And at sea level, the initial pressure is 101.3 kilopascals, right? And so there's 1,000 pascals in 1 kilopascal. And so back to this, the new pressure we experience is equal to usually our pressure at sea level plus the density of whatever fluid we are in, right? The gravitational constant, which is 9.8, as well as, and then D here is going to be our depth in that liquid. And we're going to measure depth. Oop, yeah, I want to keep those. Alright, sorry about the technical difficulties. And so what I was saying is that we are going to measure depth in meters here. We're going to measure depth in meters. There we go. Alright, back in business. And so this is a neat thing because we can talk about pressure in diving, which is something that I love to do. And so what I want to know is, what is the pressure in water that we experience at 1 meter deep and as well as at 4 meters deep? Alright, and so my question is, what is the pressure in water at 1 meter deep? And so when I think about this, right, I'm implying that I have a person who is at sea level, right, and then they jump in the water and they start swimming, and they're at a depth of 1 meter, okay? And so we know that the pressure that person is going to experience is equal to their initial pressure plus the density of the fluid that they're in, gravitational constant, and the depth that they are at, right? And so I'm assuming that this person is at sea level, which is 101,300 pascals. Plus, and then the density of water is 1,000 kilograms per meter cubed. I multiply by gravity basically to get the weight of that water, and I've got a depth of 1 meter, which is going to give me a new pressure of 111,100 pascals, right? And so if I wanted to get that to kilopascals, I absolutely would. And then I want to know, what is the pressure in water at 4 meters deep? And so I'm going to do the same thing. You already know that as you go deeper into a fluid, pressure increases, and so the number that I get here should be greater than what I found in this first problem because I'm going deeper into that fluid, okay? And so the pressure that I experience, again, we're going to assume that I'm starting at sea level, which is 101,300 pascals, plus, all right, density of water is still 1,000, 9.8 is still gravity, but my new depth is 4 meters. And so when I work that calculation out, I should get 150,300 pascals, right? Which is 1.3